Hi everyone. We have talked about section 1.6, instantaneous rate of change. Today we're going to talk about 2.1, the derivative of function, and 2, interpretation. This is math business calculus, and for the section 2.1, this is the derivative of a function, and you should know that it actually like another name of the instantaneous rate of change, or in another way, I'm gonna say instantaneous rate of change equal to the derivative of a function. Okay, so you can use this form to find instantaneous rate of change of fx, and also you can find the derivative of a function fx. Okay, now let's move to 2.1 now. So definition, in the limit definition of the derivative, I can say the derivative of the function denotes by f derivative x, or someone called f prime x here, is f prime x equal to limit of fx for h minus fx over h for h approach to 0, and the limit has to be exist. So you see that it's exactly the instantaneous rate of change formula. Okay. For interpreting the derivative, I can say that the derivative f derivative of x of a function fx could be two-way. One is the derivative should be the slope of a tangent line to fx, right? So if I have the curve f of x here, right, and a point A and B, for A and B, they are like close each other in here, say like a point that the line go through, right? So at here, since we are looking for the average rate of change for 2 points that close each other like they're very close each other, like just 1 point, and we are having is as the limits of h plus h minus fx over h for h go to 0, is slope of that. So the slope of the tangent line. Okay. And the second interpreting for the derivative is instantaneous rate of change with respect to x. So exactly it is IRC, instantaneous rate of change. Okay. For the notation of the derivative, I have some notation in here. You can see that we have f prime x, y prime, dy over dx, df over dx, and d over dx f. So you should know that this is not like a fraction. The one look like a fraction here, but it's not. It actually is not a fraction. It just present for the derivative. Okay, so you don't think it's gonna be like a dy divided by dx, like a fraction before. Okay. Now let's do an example. So in here I have example 1, and I want to find the derivative of the function fx when fx equal to 5x plus 8. In here I can right away and know that the derivative function has to be equal to 5. But why I can know that's right away, I will show you later. But for now, we have to follow the way by using the instantaneous rate of change for this function, right? You should know that instantaneous rate of change will be equal to f derivative of x for by using interpreting the derivative, and it's equal to the limits of f limits of fx plus h minus fx and over h for h approach to 0. And now let's try to find all these things. So fx plus fx will be equal to 5x plus 8. So then I have fx plus h equal to 5x plus h plus 8. And then I have 5x plus 5, 8, and then plus 8. And then now I will substitute into the form. So I can substitute up here, and it's going to be equal to limits. Let me circle this out. Limits of 5x plus 5, 8 plus 8 minus 5x plus 8. Don't forget the parentheses, right? Over h. For h go to 0. And then I can simplify the top, become limit of 5, 5x plus 5, 8 plus 8 minus 5x minus 8 divided by h, and h go to 0 here. And then I can finally write it down here. Limits of this 5x gone, this 8 gone. I will change the color. I just want to change the color so people can see it easier. So 5x gone, 5x gone, 8, negative 8 gone. I now gonna have only 5, 8 and over 8. 5 go to 0, and then I can again, since these are in factor order, I can just cancel the 8 between top and bottom. So then now I have limit for s go to 0 of 5, and there is a limit of a constant that will give you just a constant equal to 5, and it's exactly the answer like I say before. Okay, so I will tell you why I can easily get the answer as 5 for this problem instead of doing too many steps like this. So that's the reason why we learn in this section 2.1. And now we're gonna learn about fundamental rules of the differentiation. Okay, so the rule in here that you have to learn is a simple power rule in this session. It is very important one. So in simple power rule, for the derivative of a simple power rule, you wanna have like for if f equals to x to power n. So in here, in this case, you know that you are having like a polynomial or like a variable with some power. Then you can apply the form as dy over dx, or the derivative will be equal to n times x power n minus 1. What does that mean? That means the derivative the y derivative in here, or the derivative, the y prime of the function will be the power, the power put down in become the coefficient multiply with the variable, and the new power become the power subtract for the one. Okay. So that's one thing that you need to know. Now I'm gonna introduce you some special case. First one, I'm gonna talk about derivative of y equal to x. So in this case, the function is just have only an x, not having like a like like some power, but in here it actually have like power one at one. Okay, it actually have like a hidden power one. um, so you will actually right away can say that the derivative of a variable x is just equal to one. So why is that happen? Because when you consider like y equal to x to power one, then when you apply for simple power rule, you will have y derivative equal to one. Put it down, right? Time x to power 1 minus 1. And when you simplify it, you will gonna have 1 times x power 0. And for x power 0, you actually always know that this is equal to 1. And that what does that mean? That means 1 times 1 equal to 1. And you have y prime equal to 1 in this case. Okay? So similarly, you can easily prove that if you want to take derivative of a constant, you will always get it equals 0. And in this case, say y equals a c or a constant, you actually can rewrite it as c times x power 0, right? Because x power 0 equal to equal to 1. So then that is a reason why you can have y equal to c. And when you take derivative of that, you if you consider x power 0 here and put that 0, you can easily to have something like y prime equal to c times 0 times x power 0 minus 1. But since there is a 0 here, everything multiplied with 0 going to be equal to 0. So y prime has to be equal to 0 for this case. All right. And then the derivative of a constant time a function. So this may be applied with you many times later. You just gonna it just can move. It just can move out c to outside of the derivative, and then just take the derivative of the function. Okay. And for the case number 4 here, which is a derivative of a sum or a difference, you can just split it to be sum, or to be like instead of having one derivative of a polynomial, now you have like many term derivative, and then you can take the derivative of each term here. But keep all the sum or difference the same before. Okay. Now let's try to do one example to see what happened. First thing, in problem 4 here, 4a here, I am having y equal to x squared, and I want to find dy of the x is a derivative of y, right? Y prime in this case. So I can just apply the simple power rule for this function. So I move down the power 2 here in front of the x. It's going to be equal to 2 times x, right? To power 2 minus 1. So I'm going to have 2 times x power 1. And simplify, you have 2x. Okay? And that should be the derivative of y. All right? Now for b, similarly, you can easily get derivative of x going to be 5, put down, x power 4. Okay? Because 5 minus 1 equals to 4. Maybe I'm going to have one more step for you. So you should have 5 x power 4. And lastly, I have y equal to x, and this is like a proof for the first special case when y equal to x here, and you get y derivative will be equal to 1. I did prove it, so you can easily get that equal to 1, right? For example 3, you see that for problem A, f(x) equal to 4, which is a constant, and since it's a constant, then right away you can say f derivative of x equal to 0. Okay, and now I'm gonna come to B. In this problem B, I have f(x) equal to -16, and I want to find f derivative of 2. Okay, so it's maybe gonna try to trick you a little bit, but actually, firstly, you had to find the f derivative of x first. And since this fx is a constant number, then f derivative of x equals 0. And again, since f derivative of x equals 0, then whatever input is going to be, say f derivative of 2 will always still get 0. Okay. Let's move to example 7 here. I have fx equal to 4 over x power 8. Okay, in this problem, maybe you will say, oh, x8, x power 8 now become like a denominator or fraction. Then how can I apply the simple power rule for these problems? You may not, if you don't know how to change this fraction form to be power form, right? To be exponent. So I mean, I will change the fx to be. Once again, I'm gonna move this down here. So I'm gonna change fx. I would like to rewrite fx as 4 times 1 over x power 8, right? And if you still remember in correct algebra, everything like say 1 over x power a will be equal to x to power -a. Okay, everything in the denominator with every variable in the numerator with some power. If you want to change it to be not a denominator, to be a numerator, then you have to make it opposite sign for the power. So now I will have 4 times x power -8. So this is like a remark. Okay, and now since now I have this, then I can apply f derivative of x from now. in here I have like 4 times with a polynomial or like a function, right? So when I take f derivative of x here, I can take 4 out. I have to keep, I mean, I want to keep 4 out, and I just take the x negative 8 derivative of that. So then you can just keep the 4 out here, and then multiply with the negative 8 down, and then x power negative 8 minus 1. And then lastly, you're just gonna combine everything. Say 4 times negative 8 gonna be negative 32. You know what? I need some more space, so I'm gonna get down here. Right here. So I'm gonna put equal to negative 32 times x to the power negative 9, right? And if you don't want to have like a negative power, you can change it to be positive by make it become reciprocal of that. So you're gonna have negative 32 over x over 9. Yeah, I need some more space, so 32 over x to the power 9. Okay, so this is the answer of this problem. All right, so yep, so that is a answer for example 7. Come to 8. I noted that y, in this case I have y equal to cx, and they given me c is a constant. So I will apply the case that's a constant multiplied with a function up here, right? So again, you're just gonna keep the constant and take the derivative as a function. Okay, so let's go back here. But in this case, the derivative of the function in here is actually the x. So the derivative of x is should be equal to 1 by the case number 1, right? So right away you're gonna have y derivative will be equal to c, right? Because x derivative will be just equal to 1. So now, for example 9, similarly, but problem A that give you y equal to 8x, and then you actually, again, you can still apply like a constant multiply with a function, and function in here is x. So I mean, I'm gonna just keep 8 and then take the derivative of the x here, and then I'm gonna have 8 times with 1, which is 8. Okay, or from example 8 there, I can try way say that the derivative of the ax equal to 8. Okay, and b, you now can know that you're just gonna have negative 14 because you know a constant multiply with a function, and function in here is I. Okay, move to example 10 here. You have like a 1, 2, 3, 4 term of y, and you want to find the y derivative. Okay, you want to split out for each term. It can be like 5x cubed, and then take the derivative of that, plus 4x squared, take the derivative of that, and plus 9x, you take the derivative of that, and then minus 7, you also take the derivative of that. And you have to apply for each term here, in order to well, for each term here to get I mean for all the case that's satisfied for each term in here. So for the first term, you can apply the multiplication between um, a function and a constant, right? So a function in here is x cubed. So I can just keep number 5 and I put down 3. So I multiply by 3, and then x power 3 minus 1 equal to 2, right? And then I plus with 4. I keep 4 because it still is a constant, multiply with a function, and then I multiply with the power 2, and then I multiply by x, and then change the power by minus 1, and then plus for this 9x going to be equal to 9 according to example 9 and 8 there, and then a minus for 0 because a derivative of a constant becomes 0. And lastly, I can simplify. Okay, so lastly, you can simplify y prime become 15 x squared plus 8x and then plus 9. So that should be the derivative of y. Okay. Now move to example 12. I have a radical function in here. So maybe you guys are gonna think about, oh, how can we apply the power rule in radical function? Again, you still have to change the radical to be power form. Okay, so if you forget some properties of the radical, I'm gonna remind you now. Give me 1 second. So you should know that. Let me mark here. You should know that. Like a square, no, not square, a root n of x power m will always can be rewrite as x to power m over n. And you can see that the index of the root, where is my color? I will change the color. The index of the root in here is n. Is always is the denominator of the power. Okay, you have to remember that in order to change from the radical to be a power rule, a power form. Okay, so now come back with the cube root of x squared there. I can change the y 9 as cube root of x squared become 9 times x to power 2 over 3, because remember the index of the root become the denominator of the power, right? So now I will take the derivative of y by using simple power rule. For this case, again, this still a constant multiplier function. So I keep the constant and then I multiply by the power, put out the power, and then I have multiply by x times with the whole power, subtract for the 1. And let me try to simplify this. I have 9. And when I have I can cancel, I cancel this 3 by factor 3 out from 9, and I can and then I have 3 times 2 become 6 and x to power 2/3 minus 1. Okay, now maybe you can do like a side work, right? So 2/3 minus 1, what is that equal to? I have 2/3 minus 3/3, right? 1 becomes 3/3, and then I'm gonna have just negative 1/3. Okay, so now the power has to be negative 1/3. And if I want to convert it to be um, not in you know what, I just gonna keep this as the answer. You don't have to change it to be a positive power for this case, because they don't ask you that. So I just want to be lazy and stop here. Now for example 6, this is like a special example, and that's to me that's very important for you if you consider taking calculus 1 later. So you are trying to find the equation of the line of the tangent line for the curve fx equal to 1x4, and then add point negative 1 over negative 1 1. And in here I give you a hint is we have a point negative 1 1, and all we need is the slope of the tangent line at this point. Okay, and how can you find the slope at this point? You have to remember that from the definition of the derivative. What is the definition? You know that a derivative is the slope of the tangent line, right? So you take you take the derivative of fx, then you will have the slope of the tangent line. Okay, so first thing, you need to take the derivative of fx. In this case, actually, you need to change the fx to become power form first, right? So I have fx equal to 1 over x4, and I change it to be power form as x to power negative 4. You should know that. And then I'm gonna find the derivative of fx equal to negative 4 put down times x power negative 4 minus 1, and now I'm gonna have negative 4 times x power negative 5. Okay, so that is a that I can say is general slope of tangent line. Okay, now I say I want to find a specific slope at where at point negative 1 1, right? Which mean x equal to negative 1, right? I have the slope of the tangent line will be slope m equal to negative 4x negative to power negative 5, and I substitute the x become negative 1, so I have negative 4 times negative 1 to power negative 5, and that will give me still a negative 1 times negative 4, then you're going to have 4. Okay, now you have slope of the tangent line already. and in order to find the equation of the line, of the tangent line, you need a slope of the tangent. Okay, you have slope, and you need to have a point, right? And if you have a slope and you have point, then you want to apply the slope. So let me type it better. So I'm gonna apply or substitute slope equal to 4 and point -1, 1. Remember that this point is the point that tangent line go through and touch the graph of fx. So this point is lie on the graph and also lie on the tangent. I'm gonna draw like a here's I assume this curve of fx here, and that is a point. Say point -1, 1 is here, and the tangent line is just go through and go through this point and touch the line at -1, 1. Okay, so I say so now I'm gonna say into plot slope form. If you still remember plot slope form, y minus y1 equal to m times x minus x1. You can easily apply that by y minus y1 in here is what is 1. Okay, again, let me notate it. So here's x1, here's y1. Okay, equal to m is 4 times x minus x1 is -1. So now I can simplify it as y minus 1 equal to 4 times x plus 1. And I can even stop here because the question just asked me for the equation of the tangent lines. This is a this is the equation the tangent line in the plot slope form. You don't have to worry to you don't have to change it to be slope in the same form because they don't ask you to do that. So just try to make this. I just try to save my time and you too. Okay. So this should be the answer. All right. Now, one more thing that you need to know is a marginal change. In maybe in the business, the word marginal maybe something like marginal profit. You should understand that it means that it is an approximation to the actual change, and when you talk about marginal change, you actually gonna take the derivative of the function of the things that you are talking about. Say marginal profit, then you want to take the derivative of the profit. Okay, so let's do example 13. If y equal to 6x4, you will they want you to find the derivative of y, and then find the derivative of y when x equal to 3 and finally interpret the result. Okay, let's do it. So I have y equal to 6x 4, right? So then you can right away say y prime will be to what? 6 times 4 x to power 4 minus 1. Okay, and then simplify everything. 6 times 4 is 24 times x power 3. Okay, so this is y prime. Now since you have y prime already, they want you to find dy dx for x equal to 3. What does that mean? At x equal to 3, they want to find the y prime value. Okay, so we have let's move down here. Dy dx for x equal to 3 equal to 24 times 3 to power third, right? So I have this one I need to use my calculator. So 24 times 3 to power third, and then enter. I have 648. So 648 is answer. So in order to interpret the result, you're gonna say if the value of x increase 1 unit, okay, in value from x equal to 3 to x equal to 4, because it's increased 1 unit, then okay, fx or the y will increase approximately. Okay, in this one we are doing approximate for the actual change. I know that maybe some of you are gonna do fx when x equal to 4 minus fx when x equal to 3 to get the increasing like perfectly accurately, but we are trying to figure out a way to find the approximate number. Okay, so in this case I have that the answer is 648 units. Okay, so yeah, sometimes we need this for the real life, because you cannot approach you cannot have you cannot have like an actual number for the future, right? You can just have approximately say you're gonna approximate your income for next year. You cannot know exactly what is that for at this time, but you may use derivative like a approximate to get the income in the future. You know your income depend on a function. Okay, so now let me come to example 14 here. Okay. Health officer concerned with a flu epidemic that has hit the North Atlantic coast have estimated that the number of people ill with flu symptoms can be approximated by a function. Okay, so I have this function, and t equal to 90 t squared minus t cubed. For t had to be 0, between 0 and 70. And t measure in days, okay, since in the beginning of the epidemic. Okay, so the question is, how many people have the flu on day 15? What does that mean? In this case, t equal to 15. What happened? Okay, so you can easily do this by substitute into NT, or you're gonna get N of 15 will equal to 90 times 15 square minus 15 cube, and you will get you're gonna pull out the calculator and just gonna using that multiplied by 15 square. No, not 12, it's 15. Okay, and then you minus for 15 to power 3, and you're gonna get answer as 16,080.75. Is that correct? Let me check. Yeah. Okay, so that is people have flu on day 15, okay, or like after 15 days, see in the beginning, okay. Now, at what rate are flu symptom spreading on day 15 of the epidemic? Okay, so so in this case, you are looking for the changing. Okay, you are trying to figure out how much is increasing or decreasing after 15 days. Okay, so in this case, I'm gonna put down B here and say I have to find the derivative of NT for T equal to 15. Okay, so I'm gonna find out N derivative of T first. And okay, let me notate for problem B, we actually find N derivative of 15 equal to what, right? At first, I had to find out derivative of NT, which equal to 90 times 2, and then T to power 2 minus 1, and then minus for 3, and then T to power 3 minus 2, and then simplify, I have 180 times T minus 3. Oh, why I have minus 2 here? It's V1. Okay, and then T to power 2. Okay, and now I'm gonna have N divided of 15 become, using this general derivative, I'm gonna substitute T become 15 minus 3 times 15 square, and that's gonna give me using a calculator again, and I have 180 times 15, and then minus 3 times 15 square, and you will get 2025. Okay, so 2025. Oh, I forgot the number. 25. 25. Okay. And what does that mean? So that mean what? That mean from since day 15 is the rate or I say the people getting flu is increasing about 2025 people from day 15 to 16, right? So the interpretation. So on day 15 of the epidemic, there are 16,875 people ill with flu symptoms. And if it increased by one from 15 to 16, the NT is increased by approximately 2025. I forgot the word approximately last time, so don't forget that. Okay. And lastly, problem C, when the flu symptoms spreading at the rate 1,500 people per day. Okay, so in this case, they're giving you like the rate of the rate of 1,500 people per day. So what should I do? I actually will come back with the general form of the rate or of the derivative of t, which equal to 180 t minus 3t squared. And then I know that in the given from problem C, it's given me that n derivatives. I mean, at the case the rate is 1,500, so I change n derivative t equal to 1,500 and equal to 180 t minus 3t squared. So at n derivative t equal to 1,500. Okay, that's from given, right? So now I'm gonna try to solve this equation to get the value of t, right? So in here, it looks like I'm having a quadratic equation. Let's try to convert it to be quadratic form. So I have, say, both inside by 3t squared and minus 180t. So I have 3t squared minus 180t and then plus 1,500 equal to 0. Right? So move out this one. Okay, so now I will have let me divide by both sides by 3. I will get t squared minus 60 t and then plus what is that in here, 500 equal to 0. Okay, so yep, everything is look good. Now I would like to, for this guy, for this solution, you may use one of 3 methods from the correct algebra. So AC method, converting square, or quadratic. I usually would like to apply AC method first because to me, if you can factor, then then you solve it very quick. So A times C equal to 500 and B equal to -60. Two numbers that multiply each other equal to 500 and then addition equal to 60. So, and also in here A equal to 1 special case. So I would like to have what is that gonna be? Say 5 and 50 and 10. Yeah, 50, -50 and 10. And then 10. Okay. So it's gonna give me t minus 50 as an on factor, and the other is t minus 10 equals 0. And now easily you can apply zero factor method to get t minus 50 equals 0 or t minus 10 equals 0. And then finally you get t equal to 50 or t equal to 10. Say 50 years, right? And 10 years. Because it's talking about like after how many years. Yeah. So that is the answer. Lastly, this is a condition for non-differentiability. These are 3K that's these are 3K that you cannot take derivative. Okay. First case is if you see that fx is not continuous at x equal to a, then you cannot take derivative for fx when at x equal to a. Okay, so you cannot take derivative for this case. Okay, for this condition. So the first one is when mx is not continuous at x equal to a, then you cannot take derivative of fx at x equal to a. The second one is fx has a corner. So look at the figure 7 at x equal to a. You see that, or here, you see that there is a corner when on the graph, so you cannot take the derivative of fx when x equal to a. Okay, and that is the second case. And the last one is fx has a vertical line, a tangent line at x equal to a. Note that the vertical tangent line in the leftmost graph occur where there is a curve in the graph. So look at the figure 8 here. You see that if you have like the graph have like a curve, then you cannot take a derivative at that point because the vertical tangent line because you have a vertical tangent line, so that doesn't that is it's just become like do not exist in this case for the derivative. So these three cases cannot give you a derivative at the specific value of x. I have finished session 2.1 today. This a little bit long, but just keep in mind that this session will be very important for this class. So take your time and I see you in 2.2 next week. Have a good weekend. Goodbye.